and welcome to today's PAVE virtual panel, AI for AVs. Artificial intelligence is an important piece of the puzzle for understanding how autonomous vehicles work, and today we're going to give you a detailed look at that relationship between AI and AVs. My name is Tabitha Colter, and I'm PAVE's Director of Operations and today's moderator. I'm really excited to get to moderate this conversation with three stellar guests. First, we have Mohammad Musa, founder and CEO of Deepen AI. Mohammad, thank you so much for joining us.
Thank you. Glad to be here.
Second, we have Patrick Musau, PhD candidate at Vanderbilt University. Patrick, good to see you today.
For having me.
And our third guest is Dave Tokic, VP of Marketing and Strategic Partnership for Algolux. Dave, appreciate you making the time.
Yeah, looking forward to the discussion.
So we have to start off with the really fundamental question of what is artificial intelligence? Mohammad, could you start us off?
Yeah, definitely. So there are a lot of opinions, but we'll try to keep it simple. Artificial intelligence is basically machine thinking on its own and being able to make decisions. The types of artificial intelligence can be divided into different technical approaches. One segment of artificial intelligence is machine learning, meaning that the machine is able to look at historical data and be able to infer better decisions based on heuristics that it learned from in the past. Another type of artificial intelligence is what we call traditional decision-making or programming, where you just tell the machine, if you see this, then do that. And that's kind of a very traditional programming where just a human tells the machine what to do and the machine doesn't have any authority or like any capacity to make decisions on its own. And when you get to learning, it basically simulates human behavior, where it tries to bring all of the knowledge that it has learned from past interactions and make decisions based on that.
Great. And how do we teach machine learning programs? Dave, where does that data come from?
So the data for teaching the systems generally comes from whatever the application is. In the case of automotive, you want to be able to capture information about road scenarios, the types of objects on those roads, such as cars and trucks, signs, traffic lights, as well as pedestrians and other objects that could be interacting with a vehicle. And for machine learning, that tends to be actually quite a significant amount of that data. You need enough different views, poses, sequences of events of these objects to be able to effectively create what's called a data set, a set of data of this data that can then be applied to train these artificial intelligence models to really identify those things, those objects. Other types of learning is being applied also towards the control of vehicles, like decision making, such as, should I plan to go forward until I get to that open spot in the next lane? So things called planning and control. So artificial intelligence is also being applied there, in addition to more, I'll call it traditional control type algorithms that have been done in the past.
Great, really helpful. And just to sum up a little bit, so machine learning is an application of artificial intelligence that's enabling the machines to learn and improve from experience. One phrase I know we often also hear a lot is deep learning or deep neural networks when we talk about AV development. Patrick, could you talk about how that fits into this outline we've created so far?
Yeah, sure. So deep learning is really a branch or subset of machine learning that draws inspiration from a set of models known as artificial neural networks. And these models are very loosely modeled after the biology of our brains that's designed to recognize patterns as well as perform other functions. So you can imagine in your brain a large set of neurons interacting as you make a decision that you're particularly concerned about. And within deep learning, what we're really concerned about is constructing mathematical models that are able to mimic these behaviors on sensory data. So images or just sensor information from the vehicle's configuration of sensors. And the deep here in deep learning is really the idea that you can have a large set of interacting neurons. And as you increase the number of neurons, you can increase the types of complex tasks that they can handle. So, and typically these are tasks that are outside of the scope of traditional programming. So identifying pedestrians, predicting where those pedestrians will be, or even labeling the drivable region for the vehicle within its environment. And over the last couple of years, we've seen these models really revolutionize the types of tasks that we can handle from classification to object detection, achieving near human levels of performance. So it's really exciting within the context of autonomous vehicles.
Great. Any other kind of foundational information people might want to know about AIs before we start digging into how they work in AVs?
Well, I think maybe one. Oh, go ahead, Mohammad.
Go ahead, Dave.
No, I was just going to make one comment that the types of activities that are being applied by AI today have been done in what's called more classical or traditional approaches for decades, actually. But it's been really fascinating to see the progression of accuracy and performance and so on that AI has brought to these particular tasks. It's been kind of this step function of improved performance and accuracy, et cetera. And so these approaches work really well, right? And I think, you know, again, maybe one comment is it's targeted at particular tasks. So I know people say, oh no, AI is going to take over the world. It's not really true. It's like, oh, can I really identify that fuzzy looking image over there is a person or a vehicle? And, you know, it'll tell me yes or no with a lot more, you know, accuracy than maybe more classical programming techniques. So it won't take over the world, but it will help us actually be much more able to do these tasks in a more automated fashion than we've been possibly able to do before.
And to the ability for the machines to recognize objects and infer situations and context, that training relies on giving the machine billions of frames, or, you know, on the lower end, maybe at least millions of frames that are annotated by humans to tell them, oh, here's what a human looks like from this angle, at daytime and nighttime, and in rain and snow, etc. And the same thing for every class: vehicles, traffic signs, traffic lights, buildings, pedestrians, dogs, cats, etc., etc. And this process is like, AI is still very, very far away from being super versatile. Like you show a baby a cat that looks somewhat different than all other cats, and they will infer that it's a cat, but that's not necessarily the same with AI. And mathematically speaking, we call it a slight difference in the input of the data can cause an extreme misclassification or misunderstanding in the output of the AI system. So like you give a traffic sign that is a stop sign to an AI system, and you make some changes onto it, the machine may recognize it as speed limit rather than a traffic sign, rather than a stop sign. And so there is a lot of work that still needs to be done in this approach, but the accuracy that we've been able to achieve with deep neural networks and some of the latest improvements in AI are phenomenal compared to the traditional methods that they've talked about before.
Yeah, and Mohammad, I really like the point you made about comparing the baby's perception of the cats versus the computer. And actually, that's what I was hoping to do next is think through the human perspective of driving a car, as it's something, you know, most of us here in the audience can really easily imagine, and try to compare that to a machine system. So, you know, first of all, humans, we use our senses like eyesight and hearing to observe the environment around us that includes other vehicles and pedestrians. Dave, what's the parallel to that human observation when it comes to an autonomous vehicle system?
Great. So the human brain and our sensing systems are really incredible, right? You may have learned how to drive in New York City, and then you go out to the country, and you know you can still stay on the road and make it to your destination, even though there's not tall buildings around and you know it's not packed with traffic. Or go to a different country, and you know, yes, maybe you can't read the signs, but you kind of know how to drive, right? And to Mohammed's point about, you know, it doesn't take you very long to know that that cat is a different cat, but it's still a cat, right? And so the way a vehicle today would sense a particular object, and we'll call it a pedestrian or, you know, a traffic sign, as Mohammad had used as an example. Vehicles are comprised of multiple sensors. The cars that you drive today typically have 3 sensors: a camera, some ultrasonics to give a bit of range, and you may have a car that as you're parking, it kind of beeps if you're getting too close to the curb or something like that. And some cars also have radar as well, which allows further distance. And these sensors allow us to capture information about what's going on around the vehicle as data that can be then used by the algorithms to provide a driver warning. For example, there's a stop for a vehicle in front of you or a pedestrian, or you're kind of getting out of your lane, and maybe the steering wheel will shake a little bit to tell you to get back in your lane. And maybe both the ultrasonics and the radar are using different ways to determine distance. So ultrasonics use basically very high frequency sound to like a bat or a dolphin or something like that to bounce off of an object and then measure like how far that is. And then radar will use basically electromagnetic waves, like a radio, to then determine and bounce that signal generally to farther distances than ultrasonics can go. And then people really understand cameras well, right? But if you think about it, a camera is using a digital sensor, which everyone has multiple on their cell phones. Oops, didn't mean to do an advertisement there. And that sensor basically will capture light, the photons that are coming in, and transfer that into electrical signals that will then be inferred. For us, when we look at something, we're actually taking those photons into our eyes, and our rods and cones in our eyes then translate into our optic nerve to then be inferred by our experiences to say, oh, that's a tree, and that's a cat, etc. And we learn that really quickly. Putting yourself into how these digital systems work is that the camera sensor will capture frames. So, maybe 30 frames a second or something like that. Each one of those is a big bunch of ones and zeros that someone has to say, hey, this row of zeros and 12 ones and another 8 zeros and so on, that means tree, right? So it's this really, going back to what Patrick and Mohammad said about AI and training, you have to get a whole bunch of these things, these images, draw something around that person or sign or vehicle and tell it that's a car, that's a vehicle, or a tree, or excuse me, a pedestrian. And then after telling it a whole bunch of times, the system then infers that that is a person the next time it sees those patterns. So you can kind of look at this as taking this data that these sensors on your vehicle get in, and then doing some pattern matching or pattern recognition and assigning it a probability that, yeah, that's 98% sure that that's a pedestrian. Hopefully that helps. Is there maybe more clarification you're looking for?
No, that was a really great overview. Yeah, and so then, building off of that, so as that human driver, we use that information we've collected about the environment around us to make decisions, as you're mentioning, like when do we turn? Do we need to go ahead and slow down for that pedestrian? Make those decisions. So yeah, then Patrick, how does an autonomous vehicle make those decisions using the information process that Dave described?
Yeah, I think just building off the previous answer, there's really 3 questions that you're trying to answer when making decisions. It's the perception piece, what is my surroundings and what is the current state of the vehicle? Then you have these planning components of what do I do with this information? And then this final piece of control is actually how do I get the vehicle to do what I actually want it to do? So frequently this perception piece is you have a large set of models that's interpreting information from all of these sensors. And typically there's some redundancy between these sensors because different sensors have different efficacy in different regions. So you might have a machine learning component that's interpreting images from the camera, detecting, for example, that tree that was mentioned previously. You might have another model that's actually classifying where the vehicle can traverse within the environment. And then another one that's predicting how pedestrians are going to move within the environment. And then based on those things, you typically pass the outputs from the machine learning models to classical components such that have been developed in the automotive industry for years. So how do you come up with plans to move around those things? And then this final piece is, with these plans, is it physically realizable for my vehicle to do that? What are the steering inputs that will allow me to get to the state that I want to be? Or what are the throttle inputs as well? So it's really this nice intersection of 2 fields, of this AI piece of understanding where I am in the world and what's going on around me, and this classical piece of how do I get the vehicle to actually do what I want it to do.
Yeah, and maybe one thing to add, just from a sensing perspective, as we kind of go to this path towards autonomous vehicles. Today, with human-driven cars and the camera, radar, and ultrasonics, the driver is still in control. You know, even with vehicles that have some level of automation that are on the highway today, whether it's a Mercedes or Tesla, et cetera, the human's always in control. But as you get to more automated and autonomous vehicles, which I think is a really key point, is that we're handing that control over in certain scenarios up to all scenarios to the vehicle itself. And therefore, while in the driver assist world, you can get away with fewer sensors, maybe even just a camera. But in the to Patrick's point, as we move towards automated and autonomous vehicles, you need multiple sensors to make up for deficiencies in each one of those sensors. And that's where you start seeing a lot more of what's called LiDAR, which, like radar sending out electromagnetic pulses, like a radio, LiDAR sending out laser pulses to do similar distance and ranging. And so all these systems have their pros and cons in different conditions. For example, if you're sending out laser beams and it's really foggy out there, you get what's called backscatter. So the light just kind of scatters in the fog droplets and really you don't get a good return, whereas radar can see really fine through fog. Cameras themselves are kind of like human eyes. You know, if it's clear out, you see great. If it's foggy or it's dark, it's a little harder to see, but you can still do it with some good tricks. But you need kind of I would call it a suite of sensing, like humans with our ears and eyes and so on, to kind of really understand and have a good awareness of your surroundings. So I just wanted to kind of create that bridge from what we know today, most people that are driving know today, to where things are going with the more autonomous vehicles.
Super helpful. This is a really great foundation. And while we're just talking about the system and what roles AI might play there, Mohammad, are there any other roles that AI might play when we're talking about an autonomous system like Dave was just discussing?
Yeah, if you think about the journey of an autonomous vehicle or a driver assistance, the first thing is perception, which is, can I detect things? Can I classify things? That's called detection and classification. And then you start to get into more advanced levels of, can I segment things? Do I know where the lane exactly ends? Do I know what are the boundaries of the road? Where is that traffic sign is exactly, like segmenting it in both time and space. So I know where the boundaries of those humans or signs or lanes or other vehicles on the road and so on. Once you're done with segmentation, you go to tracking, which is, where is this car? Where was it in the past? And how is it moving? Do I know the velocity? Do I know the trajectory of this person or that vehicle next to me? And then you get into prediction, like, what is this vehicle going to do in the next few seconds? Will it be in front of me? Is it am I at risk from it? Is this person acting rationally? Do I need to avoid them? Or like, oh, we have eye contact, so we know that I can go without actually waiting for them to cross the road, or things like that. So there's all of these things that we as humans negotiate subconsciously, and we get signals about how to behave. Machines need to do that very explicitly. And then once this whole of the perception and prediction layers are done, then there's actuation, is essentially telling the motor to speed up or slow down or hit the brakes all of a sudden. And with each cycle, you have to do that multiple times per second. So you monitor how the other agents or how the world is changing around you. So like you keep doing this again and again and again, hopefully avoiding accidents and arriving safely at destination at the end. Now, all of that happens with some AI looking at, where am I on the road? Like, am I driving according to a map? Do I have to navigate autonomously, or do I get instructions from the human in the car, or potentially someone else who's remotely monitoring the operation and making sure that things are operating safely? So all of these kind of different functions, from perception to prediction to actuation, then that feedback loop continuing with mapping, and all of the sensors, all of the hardware, all of the software stuff are happening reliably. AI can actually contribute a role in every single piece, even at like when you apply the brake. Do you apply the brake like all of a sudden, or do you apply it in different ways? How much you consume out of the battery if it's an electric vehicle, or like the gas if it's a gas vehicle. So AI can play a lot of roles in every single aspect. Our companies with Algolux and Deepen, we focus a lot on the perception, computer vision component of things, but there is a lot of other mechanical stuff that maybe Patrick can tell us about, where AI can also play a role. Yeah, there is a wormhole in every single topic, so we can go, into a lot of depth, but let's keep it at an abstract level.
Absolutely. No, and that's really helpful. And so, thinking through the fact that, as you mentioned, Mohammad, AI can be used in every single piece when we talk about autonomous driving, that kind of leads me to another set of phrases that I think we often hear kind of thrown around that I'd like to discuss a little bit. And that's the phrases assured autonomy or trustworthy autonomy. Patrick, what role does that concept play with autonomous vehicles?
Yeah, I think it's a really fascinating field. And there's been a large progress within this field over the last couple of years. But what that's really getting at is we've seen a lot of progress within the AI community of methods that can do this classification, that can do these types of object tracking. One of the main challenges is, how do you demonstrate that these models are working correctly? So how do you generate evidence that perception network will always, for example, detect a pedestrian within complex scenarios? So coming up with approaches like that is really at the heart of the Assured Autonomy program. For example, one thing that I like to talk about, and was mentioned earlier in this talk, is that if you just change a few pixels within a camera image and pass it to a perception network, there's a high probability that the network will get that classification wrong. And there's a whole suite of approaches that enable these networks to be robust to these kinds of shifts. But one of the goals of the Assured Autonomy project is, how do you come up with approaches that provably show you that the method works? Beyond that, there's a lot of different questions. How would you come up with approaches for showing that, for example, that a machine learning component will work correctly on data that it hasn't seen before? How does it detect when it's in a state like that? So coming up with these holistic analyses of perception systems, of autonomous vehicles, not just from the AI perspective, but even on the system model. So for example, if you have a machine learning model that's really good at controlling the car when the battery level is high, how do you guarantee that it will also function correctly when the battery level enters a low state? Or if, for example, one of your systems within your vehicle becomes degraded in any way. So all of these types of analyses are part of the Assured Autonomy project.
Well, it sounds like a big part of that is safety, is that concern that a lot of people have when they start thinking about autonomous vehicles. And Mohammad, you mentioned briefly, but your organization, Deepen AI, is working towards that goal of safety. How do you ensure that your AI data tools are safe?
Yeah, there is a lot of AI safety certification methods for how you develop the software, how you go about deploying it in the vehicle. There's something called ASIL-D certification for any software that runs on the car, and it goes through a lot of verification and validation methods to make sure that it's safe. With autonomy, there is a new wave of safety criteria that we've never had to handle before, because the number of edge cases or variety of input is so large that traditional certification methods do not apply anymore. And the way we're doing that along with our customers, we started an initiative called safetypool.ai, which is a database of scenarios that prove safety to an extent for an ODD. So ODD means an operational design domain. So let's call it the 101 highway from Los Angeles to Bay Area, for example. And in that ODD, it's sunny days in the summer in California. So that's an ODD on that highway. What are the parameters or scenarios that you need to prove that you can operate safely without any issues all the time within that ODD, obviously. And so with this database, we form partnerships with World Economic Forum, several governments, and several companies like NVIDIA, Cruise, and others to work on making this database as a starting point to, and I said to an extent, meaning that it's like a minimum, let's call it a minimum threshold. So if you want to operate an ADAS or an AV system on that ODD, you need to prove that you can meet all of these scenarios in the database, 100% to say that you're safe for those scenarios. Like obviously we cannot say you're 100% safe all the time because the amount of testing that is needed to do this, if you looked at Waymo or Cruise or these bigger companies, they actually have multiple data centers dedicated for testing and verifying the safety of their systems, running for years. There are billions and billions of scenarios. The safety pool is meant to be a minimum database to just say, here is the minimum competency level of safety where you can prove that you're operating, you know, like you can pedestrians, vehicles, lane changes, obviously trucks, motorcyclists, etc., within that ODD. And we do that along with different partners. I can, you know, go into more detail, but let me stop there and turn it back to you.
Is it a good way to sort of abstract that it's kind of a driving test for AI, sort of? Yeah. Just like we take our own driving test to get our licenses, this is kind of a driving test for AI.
Exactly.
Yeah, and yeah, Dave, do you have anything else you want to add there about your organization, Algolux's approach to safety with your machine learning platforms?
For sure. So we're kind of our fundamental reason for being is really about addressing this really critical issue of safety and doing that robustly and accurately through our machine learning tools. We have tools that help our customers out to help them improve their systems, as well as actual software algorithms and stacks that are embedded in the vehicles to actually do the perception task that was described earlier, basically to detect and classify the objects and the scenarios that are being used. But one key thing maybe to emphasize is this word robustness, because we've heard that a few times in the call today. And in this context, it means can the system be accurate, functional, and correct under all the scenarios that that particular vehicle is operating under. So you may know a lot of the AV companies do quite a bit of testing in Arizona because it's sunny and it doesn't rain a lot and the weather's great. But you know what happens if it's snowing or if it's foggy or it's dark out, or raining and dark, etc. As a human driver, as it's getting dark and it's raining, you're getting a lot of glare off the road, and it's kind of I can't really see the sides of the road too well. How do I stay in there? And these vehicles have the same problem. Now, the interesting thing is when you look at a picture, say, for example, a camera-based sensor on your phone shows you, hey, it's a beautiful picture from your expensive cell phone. The human eye actually has a limited what's called dynamic range, whereas with an image sensor, you can see a much bigger dynamic range of information. And so between that and the other sensors, you're getting a very superhuman kind of input coming in, and then it's really up to the algorithms, the AI based algorithms, to interpret those under those tough conditions. A great example would be, hey, I took a picture in the dark and I can't really see anything, but that camera actually can see quite a bit if you know how to kind of process that data. So it's really about making these systems very robust, being able to work under all these scenarios, and as necessary, augmenting these different augmenting the information with different types of sensors so that you get as good a set of information coming in for you to make intelligent decisions on. And that's kind of what Algolux does. We provide we train these algorithms to be able to be extremely robust. We've got some really cool ways that we handle this low light and bad weather and things like that. And that's really our contribution to make sure that these vehicles are able to have a good awareness around that vehicle, so that when that kid walks in front of a car in the dark or something like that, we are able to see it and allow that car to stop safely and avoid an incident. Maybe one last thing is that just from a metrics perspective, the amount of traffic accidents and amount of vehicle fatalities due to human error, we'll call it, and especially under harsh conditions, low light, bad weather, et cetera, is pretty astronomical. World Health Organization estimates about 1.3 million people die a year worldwide due to traffic incidents, traffic accidents, and that the rate in the U.S. has been actually growing over the last couple of years over COVID, as opposed to the decades of decline that's been going on. So there's still a fundamental problem that we're all trying to solve.
Well, and to points all three of you have made, educating the public about these kind of concepts that are fundamental, like artificial intelligence and AVs, is a big part of our work at PAVE. So these 30 minutes flew by, but really quick, I would love, Patrick, if you can kind of chime in and, what are some resources maybe that people from the audience who want to learn more about AI's role in autonomous driving systems, what would you recommend for them to learn more about?
I think there's definitely. I think there's a lot of good communities out there who are just sharing a bunch of resources, PAVE being one of them. There's the F110 International Autonomous Racing Competition that offers free resources on the basics of autonomous vehicles. The DARPA Shared Autonomy Project is discussing how we can construct evidence for generating these systems, generating safe systems. And there's, as well as just a lot of research out there that's open that people can refer to as well. It's really exciting time for autonomous vehicles. There's so much. So I'm just going to mention those rather than flood everyone with too much information.
No, that's great. And that does bring us to the end of time today. So thank you, Mohammad, Patrick, and Dave for joining PAVE and our audience for this topic.
Everyone.
Great. Thanks, everyone.
Thank you, guys.
Thank you, Tabitha.
And if you want to follow up with PAVE or any of our panelists today, just please reach out to us via our website at www.pavecampaign.org or any of our social media accounts at PAVE Campaign. I will be sending a link out later today to everybody who registered that includes this full recording on YouTube and a link to our new podcast if you prefer to get your AV information that way. Thank you again to our live audience for attending, submitting questions, and spreading the word. We hope to see you next week for our next live panel, where we'll discuss why the best question to ask about AVs might not be when will they arrive, but instead, where will they arrive? Have a wonderful rest of your day.